All right, we're going to talk about projectile motion today. All right, so projectile motion is the specific type of motion that you see in A levels, right? Yeah. And what it means is, if you're really going to keep it simple, it's bah, manush bodwa diche, pet kharap hobe. If you want to keep it really simple, projectile motion is just when you throw something. So you can throw something straight up, you can throw something like this, you can be on a ledge and you can throw something like this, right? You could be, I don't know, on top of a hill or a mountain, and then you can throw stuff like this too, and it's going to go like, keep going like this, all that, right? So all of these are different types of examples of projectile motion. So now, these are all different types of scenarios where you throw something. Now what I'm going to do is, we're going to talk about a specific scenario after scenario. We're going to use examples to figure stuff out, right? First of all, what we're going to do is we're going to talk about, say, we take an object, a tennis ball, for example, and we throw it straight up. So what's going to happen? If you throw it straight up, it's obviously going to fall back down again, right? So about its motion, let's figure out a couple of things. So it goes straight up and then falls straight back down. So just to simplify things, what I'm going to do is I'm going to draw it like this, right? I'm giving it a horizontal component, but I'm ignoring it for now. Basically, I'm going to assume that this is me throwing something straight up and then falling back down. The reason I'm spreading it out like this is so that you can understand that there's an upward part and a downward part and a top and everything, right? So we start from here. So as it's moving up, right, there are forces acting on the ball. Maksud, can you tell me the forces acting on the ball?
Just gravity.
Yes, gravity is not a force, all right?
Gravitational force.
Gravitational, don't say gravity, all right? That's like the most retarded thing you've said today. And you say a lot of stupid stuff, isn't it?
Sorry.
Yeah, I'm just trying to apologize.
Educational purposes, like, I make a mistake and then it comes up and then you can tell them.
Good save, Maksud, yeah. Good save.
I did that on purpose.
Yeah, sure, yeah, all right. Anyway, we're going to use colors. So, for example, you said one of the forces was gravity. I will correct that and tell you that it's supposed to be force of attraction or force of gravitational attraction or acceleration due to gravity, whichever way you want to word it. Basically, it's not just gravity, it's actually a force. So we can say that the force of attraction due to gravity is mg, right? So as the ball moves up at different points, I'm going to use red to show the gravitational force of attraction. So say, for example, we have the ball here too, right? Say this is position A, this is position B, and say this is position C. So, can you tell me about the gravitational force of attraction at the different points, Maksud?
It should stay the same.
It should stay the same. Why should it stay the same?
Because it's constant.
But
there's nothing else.
But the ball is moving, Maksud. Why is it staying the same?
That's the only force acting on it throughout the whole action.
No, there are other forces acting on it.
We're going to ignore resistance and everything, right?
Oh my God! Why are you
complicating things?
Why are you like this? Anyway. But yes, there is only one force acting on it right now, and that's air resistance. So, gravitational force of attraction. Yeah, so that's constant. So a constant force, if we write, oh my God, I'm going to confuse myself with these colors. W is equal to mg, or F is equal to ma. Let's write F is equal to ma. Can they see that? It's a little too bright, I guess. But anyway, resolution is dropping.
Really?
Yeah. So F is equal to ma. Then what happens is, you can say that the acceleration is g, right? And W is the force. W is equal to mg, right? So g remains constant. The acceleration due to gravity remains constant at all points. And the force, which is basically the weight, also remains constant. So that basically means what? That you have a constant acceleration downwards at all points. I'm using blue to represent acceleration. Red is the force due to weight. Blue is the force. Blue is the resultant acceleration, and basically the black is the path that it takes. So what this actually shows us is, if we ignore air resistance, there's only one force acting on the ball throughout the entire flight, right? And that one force is weight. Very good. Better. You're learning, man. So now the thing is that let's give it an initial velocity upwards. All right. Man, I'm loving these colors. I'm going crazy.
Purple.
Purple? Yeah, I'll keep purple too. I'll make up something to use it for. I'll just keep it in the frame right there. Like, oh look, there's a purple felt tip pen right there, and also yellow here. Oh man, this is like crazy arts and crafts, right? So let's give it an initial velocity upwards. All right? How? So like say 30 meters per second. So that basically means I threw the ball up at 30 meters per second. So acceleration due to gravity is a constant value. Can you tell me how much that is, Maksud?
9.81.
That's right, 9.81. In your O levels, apparently you don't have the ability to work with two decimal places because your brain can't deal with it. So you're supposed to turn this into 10. But in A levels, suddenly your brain grows to the point where you can deal with nothing in life except for two decimal places. So that's when you start talking, saying that it's not 10, it's 9.81. But yes, I will stick to 9.81 now because that's what the standard is expected to be in your A levels. So let's draw a graph, all right? We're going to draw a graph with a purple pen. Man, this is so colorful, exciting. So this is a velocity time graph. Maksud,
Yes.
what's the initial velocity?
30.
30, that's right, 30 meters per second. And what does the gradient of this graph represent?
Acceleration.
Very good. So which way is it accelerating?
Downward.
Okay. Now you might notice something. All the accelerations we've drawn in red are downwards, right? But the velocity which we've drawn in green is upwards. So velocity and acceleration, these are vector quantities, which means if you move upwards or downwards, they're going to mean different things. So this basically means if we consider the 30 to be a positive value, then the acceleration, which is 9.81, is actually a negative value. So we'd have to write this as minus 9.81, right? Because it's downwards, and downwards is negative in our scenario, meters per second squared. You can write it like this, or you can write it like this. I personally prefer meters per second squared like this, but it's not wrong if you write it like this. So anyway, moving on. So that means the gradient of this graph is going to be how much? Minus 9.81. And will the gradient change?
No.
No, it won't change. So basically, if we take these positions A, B, and C that we initially drew, we can write that we start at point A, right? And then what happens? As the ball falls, it doesn't fall. Actually, as it's moving up, the velocity decreases. It's slowing down. Then what's happening here? Can you tell me?
That he reaches maximum height.
Exactly. Maksud, this guy is smart, man. Yeah, you're on a roll. You've been studying, haven't you? That's cool, that's cool. So yes, basically, the point here, which is basically the point where the velocity is 0, is the highest point of the motion, which is B, right? So now we reach point B, and then what happens is we can continue moving downwards like this. And that basically brings us to this point where it's point C. It's back here. So you'll notice that this is a straight line. Can you tell me with a confident reason why it's a straight line?
Because you have G, which is constant.
Excellent. Maksud, you're going to get a chocolate. Have a chocolate. Yes. Yes. So yes. So basically the gradient of the graph is constant. And why is it constant? Because the acceleration or the deceleration here is a constant value of minus 9.81. So this is going to be the velocity time graph of this motion. All right. So as we throw it, it goes up to the highest point and then back down again. And this is the graph that you're going to get. So the thing is that this shows motion along only one specific axis, right? Which axis?
Vertical.
Yes, the vertical axis. It just shows the motion up and down. So that basically means that even if this was all happening, say, on a train, right? Say this is basically someone just playing with a little ball on a train as they're traveling at a constant speed. In the person's hand, the ball's going to be moving up and down. Let's try to draw that scenario, shall we? So let's say we have empty paper. I'm going to try to use the paper efficiently. I don't want to waste paper, right? So say we have a train. I'll use the black felt tip again. So this is the inside of a train, and the train has seats, right? And like, you know, people are sitting and talking and stuff. So there's this person here, and they have a ball, and they're just playing catch with the ball. Basically, they're throwing it up and down, up and down. You can do that in a car also, by the way.
Oh.
So like, you know, if you throw a ball when the car's moving forward, will the ball hit your face?
No.
Well, if you throw it at your face, it will hit your face.
It will.
But if you throw it straight up, then it won't, right?
It won't.
Okay. Yeah, Maksud's getting a
The more
little
you know.
tired.
The more you know.
Yes. Okay, moving on. So basically you throw it up and throw it back down. But the interesting bit is, say, for example, this whole thing moves in this direction, basically the whole train's carriage. By the time he throws it and it comes back into his hand, the train's carriage has moved a certain distance this way, right? So does that mean that the ball stays here? No, not necessarily. What's happening is the ball is moving up and down. Say it takes a time of, say, 0.2 seconds, all right? Say it takes 0.2 seconds to go up to the highest point and come back down in his hand. So within this time, he's reached, in 0.2 seconds, he's reached this position. So he's still sitting on his chair. And relative to the train and everything, he hasn't moved. But if we're watching it from outside, or a stationary observer, he's going to see the train move from here to here. So the path he sees the ball to take is going to be different. Let's use a different color. The path he sees is something like this. Right? Oh, man. Oh, I tried, guys, I tried. So basically, you get a projectile motion. So he threw it up, it came back down again, but as the train is moving at a constant velocity, you see a path which is more parabolic, right? So you see this parabolic path. And the reason it has become parabolic is because now we have two components. We have a vertical component and we have a horizontal component. The vertical component, please remember, is exactly what we talked about right here. The vertical component doesn't change, no major changes or anything of the sort, right? We still have this sort of graph. We still have this sort of acceleration and everything. We just move the whole thing as it's happening. So that means, say the whole thing takes a certain amount of time, the time remains unchanged. So it's just that within that time, it's also covered a horizontal distance along with it. Now, one of the important things you have to understand here is to solve these sums properly, you have to be able to split the equation along a vertical axis and a horizontal axis. So once you can do that, the equations and the work becomes easier. So instead of now talking about having the ball on a train and then throwing it like this, we're going to change this situation and take it a little further. So now what we're going to do is a different scenario. Say we go to the field. This is a field, that's why I use green. You know why I use green, Maqsood? I'm going to draw grass now. All right?
Nice grass.
Yes, thank you, I know. You know what I should draw too? The sun.
And then like blue clouds or something.
Oh, I think they can't see this. It's too light. Right? Anyway.
It's there, it's there.
It's there, right? It's there. You can see it. All right, moving on. So what we're going to do is we take a ball and instead of throwing it straight up, we're going to throw it at an angle. So this is the path that is parabolic, right? So in this parabolic path, what happens is we can split it along different axes and get different values. So we're going to use more colors for this. Give me the gray one. Yeah, the gray one. Good job, Maqsood. So I drew a tangent here. If you notice this, I should actually use a scale to do this to make it even look better. Even better, sorry. So it should be, the tangent is going to be something like this actually. Like this, all right? Ignore this one. You can't draw out felt tip, sadly. So now that means when I first threw it, the angle from the ground was this, theta. And the velocity that it initially went with was v. So if we go into a little bit of trigonometry, I know you guys hate trigonometry, but we're in physics, so surprise, surprise, we're going to talk about trigonometry. So say this is a triangle, right? A right angle triangle. So in this right angle triangle, I'm going to use a darker color so that you get it. If we want to represent what we just drew, then the hypotenuse could be our velocity, and the angle from the ground could be theta. So the side which is opposite to the angle, what the hell, man?
I'm trying to see.
you should sit on this side, like, you know.
Oh yeah, because
Marx was like this side, that side, this side, that side, this side. And every time I move my hand, he's like on that side. And then I move my hand back here, like this side, that side, this side. Anyway, yes.
I'm right.
Okay. Yeah, I'm going to ignore Maqsood now. So basically, this side represents the vertical component. Basically, this motion can be split into motion along this axis and this axis, right? You can split it along these two planes. This is being the vertical, and this is the horizontal. So we have vertical and horizontal motion. Notice that these are perpendicular to each other, and because they're perpendicular to each other, they can ignore each other. Any change in the horizontal will not affect the vertical. Any change in the vertical will not affect the horizontal because they are perpendicular to each other. This is a concept which runs throughout the entire theory and existence of physics, all right? And not just physics, but mechanics and any sort of forces. Whenever they're perpendicular to each other, you can ignore one when you're working with the other. So basically, this means that this is translated here, right? Translation means basically you take an arrow, you snatch it, and you put it here so that you can turn it into a triangle. So if this is V and if this is theta, for the theta side, this is the opposite side to the theta, right? So for those of you who might not be comfortable with trigonometry, I'm going to go into a little more detail. The angle which is opposite to the side which is opposite to the angle is called opposite. The side which is touching the angle is called adjacent. Do you know why? Because it's adjacent. And this side is called the hypotenuse. Right? So we have hypotenuse, we have opposite, and we have adjacent, right? So these are different sides. So there's these interesting ratios between them that I think the Egyptians came up with it the first time, trigonometry. Basically, they used it to make pyramids and stuff, and also, like, you know, one of them actually figured out that the earth was curved, you know, like 4,000 years ago, and we're still fighting about earth being flat. Earth being flat. Okay, I'm not going to talk about that. So what happens is, because we've drawn a lot here, I'll just draw it again. So we have theta. This is going to be our hypotenuse. This is going to be our opposite. This is going to be our adjacent. So the relationship between these are specifically called trigonometric functions. So for example, opposite by hypotenuse is equal to sine theta. Adjacent by hypotenuse is equal to cos theta. And opposite by adjacent is equal to tan theta. So a lot of people remember this by saying this thing called SOHCAHTOA. SOHCAHTOA. I have no idea what this means.
But it helps. It helps. This is how I remember it.
Yeah, sure. SOHCAHTOA, man. SOHCAHTOA. It sounds really weird. But anyway, guys, let's not get too far into the maths. Let's come back to this. So that basically means the motion v along this, the velocity v with an angle theta, can actually be split into two independent motions, right? One being vertical. I need a smaller scale. I never thought I'd say that, but I hate smaller scales, but I actually need one.
The same triggered.
Oh, I broke a scale the other day, didn't I? What? It was his trigger. Sorry, his scale, right?
Not Farazi.
Yeah, Farazi. Oh, poor Farazi. Okay. Then, moving on. So basically, this is going to be our one of our angles. So as you can see, this is this side translated from here to here. So this is opposite, right? We know theta and we know hypotenuse, so we can use this equation. Basically, opposite by hypotenuse is equal to sine theta. So if you rearrange it, opposite is equal to h sine theta, where h is velocity in this case, right? So that means that this component can be rewritten as v sine theta. That's right, Maqsadul, you're smart. And the horizontal component here can be rewritten as v cos theta, right? You get that, guys? Is everyone clear on this so far? I'm taking some deliberate time and action in explaining the components because people get confused a lot about these. So now, we're going to talk about, we can't obviously finish projectile motion today, we'll have to continue with it tomorrow. But the points that I want to mention in this is, number one, that the vertical component here is subject to the force of gravity, right? So we can go back to using our red pen because the ball experiences mg. Remember, this is a velocity, right? So it's not a force, so it's not going to cancel out with the force itself. There's only one force acting here, which is the weight. So we can draw it at different places if you want to. The only singular force acting on the object is weight, mg.
Constant.
Yes. So which means this value, v sine theta, will experience constant acceleration downwards, while v cos theta remains unchanged. Why does it remain unchanged? Because it's traveling at a constant velocity and there's no horizontal force. Ignoring air resistance, there aren't any horizontal forces. So what does this mean? This means that the only force acting is the vertical component, which is the weight. So all of the acceleration and deceleration that will occur will be occurring only to the vertical component. This is based on Newton's first and second law. First law stating that if there's no force acting on an object, it's not going to change its state of motion. That's not the exact wording. The exact wording is going to be if an object is at rest or moving with constant velocity, it continues to do so until and unless an external unbalanced force acts on it. And the second law was what? That the rate of change of momentum, F, is equal to mv minus mu by t. So yeah, I haven't memorized, well, but the way I remember the second law is, watch this.
Really nice way.
Yes, I like it.
Yeah.
I feel really cool when I do it. Yes, you should. The rate of change of momentum is equal to the resultant force, where the change in momentum is in the direction of the force. All right, this is Newton's second law. The rate of change of momentum is equal to the resultant force, where the change in momentum is in the direction of the force. That's how you remember Newton's second law. It's easy, it's beautiful, and it's really straightforward. So based on this means you're going to experience acceleration only along the vertical component, and you're going to experience nothing along the horizontal component. Why? Because there are no forces which are horizontal. Force horizontal is equal to 0, force vertical is equal to mg. So meaning that you do experience forces vertically, but you do not experience forces horizontally. So which means all the acceleration will be vertical and there will be no acceleration horizontally, which results in the final statement of the day. When you throw an object in projectile motion, vertically they experience uniform acceleration. Do you get that? Vertically they experience uniform acceleration, and horizontally they experience constant velocity. Huh? Yes, ignoring air resistance, obviously. There you go. It's as easy as that. We'll continue with projectile motion in the next class tomorrow. Hopefully again at 10:30. Very, very important points that I would like to mention before we sign off. Number one is, a lot of people have been telling us that they can't access, or they're not notified when our classes start. So we've been working hard to figure out how to let you guys know when our classes begin, and there's this very easy way. There's going to be a little bit of work on your side, and that little bit of work that you have to do is you have to subscribe. Right?
PewDiePie.
No, man. PewDiePie. Are you PewDiePie or T-Series?
PewDiePie.
Yeah, that's good. That's good. Better than T-Series. Anyway, so if you subscribe, what's going to happen is in the messenger, right? Subscribe in the messenger bot we have. So once you subscribe there in the messenger thingy, the team will notify you every day before the class starts so that you're up to date, right? But for that, you need to subscribe. Once you do that, you're automatically going to be notified when the classes start. Makes life easier for you guys, for us, and everyone. All right? So yes, that's an important point. That's the first point I'd like to mention. And the second point I'd like to mention is that please try to follow the thing, the classes. Obviously, it's not. We'll have to cover a lot of stuff, and for example, we just did the beginning of projectile motion today, so we're going to do a lot more over time. And yes, and a personal statement that I would like to add: please pray for the people who have passed away today in the fires in Bonani Tower, the tower in Bonani, and let's just hope and pray that these things stop happening. And as I was telling Maksud a few minutes ago, that instead of talking about how today's situation had problems, I'd invite anyone who could come up with real situations of solving them. Like, we were talking about why can't we develop a drone which could, put out fires, or a cannon which throws fireballs, balls which take out fire. I don't know, anything, any ideas, anything. I just don't like people suffering, watching people suffer, and feel so bad, right? It feels horrible. Anyway, guys, pray for them, pray for everyone. Let us all live a life which is safe, happy, and pleasant. Take care, guys. I loved it, especially because of the felt tip pens. They're amazing. I love the colors. There's going to be more colors now. If you guys have any complaints about the colors, we're not going to listen to them. Yes, Maksud, do you want to say anything?
Bye.
Okay, that's not very unhelpful, but yes. Right, guys, take care. It was fun. See you guys tomorrow again. Bye-bye.